here we will see about the crystal field theory. Crystal field theory. Now the crystal field theory is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from electrostatic interaction between the metal ion and ligand. Now crystal field theory, it solely depends on the electrostatic model. Okay, they consider metal atom and ligand to be ionic in nature, and their bond formation is basically due to the electrostatic interaction between the metal ion and the ligand. Now ligands are treated as a point charge in case of anions or point dipoles in case of neutral molecules. Okay, ligands, they are treated as point charge in case of anions and point dipoles in case of neutral molecules. The 5d orbitals in an isolated gaseous metal atom or ion have same energy, that is they are degenerate. Now 5d orbitals in isolated gaseous metals. The gaseous metals or ions, they have same energy, they are degenerate. This degeneracy is maintained in a spherical symmetrical field of negative charges surrounded by metal atom or ions. Okay, this degenerated gaseous metal atom or ion is maintained in a spherically symmetrical field of negative charges. Now these negative charges are surrounded by metal atom or ions. However, when this negative field is due to ligands, either anions or the negative end of the dipolar molecules like NH3 or H2O, they are neutral molecules, okay, in a complex, it becomes asymmetrical and the degeneracy of d orbitals is lifted. Okay, however the negative field, okay, this field, the symmetrical field in which they are placed, if that is a negative field due to ligands either by the anions directly or by the negative ends of dipolar molecules of neutral molecules in a complex, it becomes asymmetrical, okay, and the degeneracy is lifted. Now it results in splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal field. Let us explain this splitting in different crystal fields. So let's see the splitting of the d orbitals. Okay, it is basically the same thing, hybridization, but here we do it in the form of splitting of d orbitals. Okay, now first is crystal field splitting in octahedral coordination entities. Now here the structure will be an octahedral. Okay, now in an octahedral coordination entity with 6 ligands, octahedral means you will have 6 ligands surrounding the metal atom or the ion. There will be repulsion between the electrons in metal d orbitals and the electrons or negative charges of the ligands. So here what will happen? There will be repulsion. Okay, repulsion between the electrons in the d orbitals of metal and the electrons in the ligands. Okay, so there will be repulsion between metal ka d orbital electrons and the electrons from ligand. So there is a repulsion. Now, such repulsion is more when the metal d orbitals are directed towards the ligand than when it is away from the ligand. So the repulsion is more when this d orbital, the metal ka d orbital electrons are towards the ligand and towards the ligand than when it is away from the ligand. Now thus the dx square minus y square and dz square orbitals which point towards the axis along the direction of the ligand will experience more repulsion and will be raised in energy. Okay, so how many d orbitals we have? We have 5 d orbitals, right? What are they? 5. There are 5 d orbitals. This one will be dxy, dyz, dxz. Once these are done, we have 2 more, right? dx square minus y square and dz square. Now these two orbitals, last two orbitals, they are along the axis, right? How we will draw the axis of d orbitals? Okay, d orbitals. Now dxy, it will be, this is y and this is x, so it will be in between, right? dxy it is, so this will be dxy. Now dyz, again z and y, this will be like this. dxz, again z and x. So these are in between the axis, whereas dx square minus y square, it will be along the axis, right? Along the axis. And dz square will be it is also along the axis. So thus the dx square, y square and dz square orbitals which are towards the axis, along the direction of the ligand. Okay, these are towards the axis and in the direction of the ligand, they will experience more repulsion, okay, and will be raised in energy, and their energies will be raised. So these two orbitals, dx square, y square and dz square, they are along the ligands, or they are directed along the ligands. Hence, their energy will be raised. Energy increases. Okay. Whereas the dxy, dyz and dxz orbitals are directed between the axis, will be lowered in energy relative to the average energy in the spherical crystal field. So these three orbitals will have a lower energy compared to the average energy of the spherical crystal field. Thus the degeneracy of d orbitals has been removed due to ligand, electron metal, electron repulsion in the octahedral complex to yield 3 orbitals of lower energy, that is T2G set, and 2 orbitals of higher energy, that is EG set. This, okay. Now because of this, the degeneracy of d orbital is removed. Okay. Why? Because there is 2 orbitals in higher energy, 3 orbitals in lower energy. Okay, has been removed due to the electron metal electron repulsion. So there is a repulsion between electron metal electrons now in the octahedral complex, and it yields you 3 lower energy orbitals which is named as T2G, and 2 higher energy orbitals which are named as EG. Okay, now this splitting of the degenerate levels due to the presence of ligands in the definite geometry is termed as crystal field splitting. So this splitting, now we have 2 splits, right? 3 lower energy and 2 higher energy. We have splitted the d orbitals into 2 forms, that is T2G and EG form. Now this splitting of degenerate levels due to the presence of ligands in the definite geometry is termed as crystal field splitting, and the energy separation is denoted by delta naught. This subscription naught is for the octahedral structure. So delta 0, this is for octahedral structure. Thus the energy of the 2 EG orbitals will increase by 3 by 5 delta naught, and that of the T2G will decrease by 2 by 5 delta naught. Okay, why? It will increase by, thus the energy of the 2 EG orbitals. Why it will increase by 3 by 5? Because among the 5 orbitals, 3 are in lower energy. So their energy will be given to the EG, and it will decrease by 2 because 2 of them are higher in energy, so it will decrease by 2. Now the crystal field splitting of delta naught depends upon the field produced by the ligands and charge on the metal ion. Now the crystal field splitting, it basically depends upon the field which is produced by the ligand and the charge on the metal ion. Now some ligands are able to produce strong fields, in which case the splitting will be large, whereas the others produce weak fields and consequently result in small splitting of d orbitals. So where there is, so the field is produced by the ligands, when there is a strong field of ligand, the splitting will be large, and if the ligand produce a weak field, the splitting will be small. Okay. Now in general, ligands can be arranged in series of order increasing field strength. Okay. Now here they have explained the increasing field strength of the ligands. Okay. Now the one which is least or which produce the weakest field strength is the I minus, and the strongest one is the CO. Okay, CO being the strongest and I being the weakest. Okay, such a series is termed as spectrochemical series. So this is a spectrochemical series where from CO it, from I it increases till CO. Okay, this is in an increasing order. Now it is an experimentally determined series based on the absorption light by complexes with different ligands. Now this is formed, okay, by experimental determination of absorption of light by the complex. Now let us assign electrons in the d orbitals of metal ions in octahedral coordination entities. Now obviously the single d electron occupies one of the lower energy of T2g orbitals in D2 and D3 coordination entities. Now the d electrons occupy the T2g orbitals singly in accordance with the Hund's rule. Now here we will start filling up the d orbitals. Now the single d electrons occupies one of the lower energy of T2g orbitals. Now in D2 and D3 coordination entities, the electrons will occupy the T2g orbitals singly. Okay, now this is because of the Hund's rule. For D4 ions, two possible patterns of electron distribution arises. Now for D2 and D3, there will be only one case, that is the T2g orbitals will be singly occupied. Now this is because of Hund's rule. If there is D4 ions, okay, that means 4 electrons in the d orbitals, there are two possible patterns of distribution. First is the fourth electron could either enter the T2g level and pair up with the existing electron, or it could avoid paying the price of pairing energy by occupying the EG levels. So there are two patterns. Now the fourth electron, okay, it could either enter the T2g level and pair up with an existing electron. Since there is 4 electrons, that means it will have 3 will be unpaired. Now the fourth electron can pair up with any of them, okay, or it can avoid paying the price of the pairing energy, because to pair up there is lot of energy required. It can avoid that energy and occupy the lower EG level. Okay. Now which of this possibility occurs depends on the relative magnitude of the crystal field splitting. Now which of this will happen, whether it will pair up in T2g or it will go and sit in the EG orbital. Okay, this will depend upon the magnitude of crystal field splitting. Okay, if the pairing energy P represents the energy required for the electron pairing in a single orbitals. Now here we have given two options, right? Either it can pair up or it can go to EG orbital. That is depending upon the crystal field magnitude of crystal field splitting. Okay, the pairing energy is given by P. Let's see, if P is greater than delta naught, the fourth electron enters one of the EG orbitals, giving the configuration of T2G3 EG1. Ligands for the delta naught is smaller than P are known as weak field ligands and form a high spin complexes. Okay, when delta naught, okay, delta naught is the crystal field splitting. Okay, when delta naught is lower than P, that is pairing energy is higher than the delta naught field crystal field splitting. Okay, when P is greater than delta naught, the fourth electron which is there, okay, the fourth electron which is there, that will go into the EG orbital. Okay, now this EG orbital, when P pairing energy is higher, okay, that is known as weak field ligands and it forms a high spin complexes. If delta naught is greater than P, it becomes more energetically favorable for fourth electron to occupy the T2G orbital. So here the fourth electron will go and pair with the T2G electrons and giving you an electronic configuration of T2G4 EG0. Now ligands which produce this effect is known as strong field ligands and have a low spin complexes. Now calculations show that D4 and D4 to D7 coordination entities are more stable for strong field as compared to weak field. So from D4 to D7, okay, when there is 4 electrons till 7 electrons in the d orbitals, the coordination entity, it is more stable in strong field, okay, compared to weak fields. This is first one. Second one is crystal field splitting in tetrahedral coordination. Now we have seen in octahedral coordination. Now let's see in tetrahedral coordination. In tetrahedral coordination, the entity formation, the d orbital splitting is inverted and is similar as compared to the octahedral field splitting. Now in tetrahedral, the formation of d orbital splitting is inverted and is smaller as compared to octahedral field splitting. Now for example, for the same metal, the same ligands and the metal ligand distances, it can show the delta T, that is tetrahedral, 9/4 delta naught. Okay, consequently the orbital splitting energies are not sufficiently large for forcing pairing and therefore low spin configuration are rarely observed. Okay, so here the delta values are low compared to the pairing energy, so we can rarely see the low spin configuration. That is basically the high spin configuration which are observed. Now the G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since tetrahedral complex lacks symmetry, G subscript is not used with the energy levels. So that T2G and EG, they are basically for the octahedral and square planar symmetries because they show a symmetrical center. Okay, whereas tetrahedral doesn't have a symmetry, so the G subscript is not used for the energy levels. Now next is the coloring coordination compounds. Now in previous unit we learned that one of the most distinct properties of transition metals is the transition metal complex is their wide range of colors, right? Now this means that some of the visible spectrum is being removed from white light as it passes through the sample. So the light that emerges is no longer a white. So now they have a wide range of color. This means some of the visible spectrum is removed from the white light and it passes through the sample. So the light emerges no longer is a white. Now the color of complex is complementary to that of that which is absorbed. So the color which is absorbed, that same color is seen in the compounds. Okay. Now the complementary color is the color generated from the wavelength left over. If green light is absorbed by the complex, it appears red. Okay. Now this is the complementary color system. If green is there, then the color will be red. There are complementary colors. Okay. If you all don't know, I'll tell you all. There are complementary colors for the light. Now, if the color complementary lights which are generated from the wavelength of the leftover. Okay. Now, whatever color is absorbed, okay, and whatever wavelength is left, that wavelength, for that wavelength which color is there, that is the color which is seen. Okay. I'll explain you in more perfect thing. If the white light has a 1000 nanometer, okay, the white light is of 1000 nanometer, and I have passed this white light through a complex, and that complex has a green color, or it absorbs the green light. Okay. If it absorbs the green light, if the green light is absorbed at 500 nanometer, or if the green light is absorbed at 550 nanometers, okay, then whatever is remaining, okay, whatever nanometer remains, that nanometer falls under whichever color. That color is what we see. For example, here we can see, if green light is absorbed by the complex, it appears to be red, because green light has certain nanometers. For example, forget this. If the green light is absorbed at 400 nanometer, then how many nanometers will remain? 600 nanometers will remain. The 600 nanometers has a red color. That means the color that will appear, that we can see, is the red color. Now you got what the complementary color means. Now if the green light is absorbed by the complex, it appears red. Gives the relationship of the different wavelengths absorbed and the color observed. Now here the complementary colors are given. Okay. Now the color in the coordination compounds can be readily explained in terms of the crystal field theory. So the colors of the coordination compound can be explained by the crystal field theory. For example, the complex TiH2O6, which is a violet in color. Now this is an octahedral complex since it has 6 H2O molecules. Now whereas the single electron Ti3+, that is titanium 3+, in which there is only one electron in the D, in the metal D orbital is in the T2G level. Okay, so there is only one electron in the D orbital, and that too present in the T2G level, in the ground state of the complex. Now the next higher state available for the electron is the empty EG level. So this is present in the T2G level. If we want to transfer it to another empty this thing, then it will be the empty electrons in the empty EG level. Now if the light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from the T2G level to the EG level. Okay. Now if the light which we pass through them, if it falls under blue to green region, then the which is absorbed by the complex, if the complex absorbs blue to green color, okay, color from the region of blue to green, and if absorbs that color, it would excite the electron from T2G level to the EG level. For example, above we have seen that if the light absorbed is green, it appears to be red, right? Similar thing is here. The complex, it absorbs a blue to color, or it absorbs the light in the region of blue to green. Okay. Now when it absorbs that blue to green region ka light, what happens, it acquires energy, and that energy will excite the electron from T2G level to the EG level. Consequently, the complex appears violet in color because now it is changing its energy level from one form to another form. So it will change its color to violet with respect to how much energy it has acquired. Now, crystal field theory attributes the color in the coordination compounds to D to D transition of the electron. So it is basically because of the DD transition of the electrons. Now, it is important to note that in the absence of ligand, crystal field splitting does not occur and hence the substance is colorless. So, if there is no ligands, then the crystal field splitting won't occur. If the crystal field splitting doesn't occur, then the substance is colorless. Now, for example, removal of water from TiH2O, okay, on heating renders it colorless. Now, this TiH2O6 is violet in color. If I heat this compound, what will happen? The water will be gone because here the main ligand is water. If water is removed, it will become colorless. Similarly, anhydrous copper sulfate, it is white in color, but the moment I add water into it, it turns blue in color. Okay, now the influence of ligand on the color of a complex may be illustrated by considering the NiH2O6 complex. Okay, now how influential the ligands in the complex, because ligands are the ones which gives the color to the complex. Okay, now nickel H2O6 complex, which forms a nickel 2 chloride and is dissolved in water. If the didentate ligand, that is ethane 1,2-diamine, is progressively added in the molar ratio of 1:1, 2:1, 3:1, the following series of reactions and their associated color changes. So, nickel H2O, it is a complex. Okay, if I remove the H2O from the complex, it will be colorless. Now, if I add a didentate ligand to it, that is ethane 1,2-diamine, this is the ligand. Okay, to that colorless nickel, if I add this ligand progressively in a ratio of 1:1, 2:1 and 3:1, okay, these are the series of reaction that occurs and these are the color change that is observed. Okay, now nickel in presence of H2O as a ligand, it is greenish in color. When I remove that, it is a plain in color, but the moment I start adding the En molecules, it will change its color to purple and last to pink. Okay, these are the color changes. So nickel aqueous, it is green in color. The moment I add one En molecule to it, it becomes bluish in color. The moment I add 2 En molecules, it becomes purplish in color, and the moment I add 3 En molecules, it becomes pinkish in color. Okay, so the color changes the moment I change the ligands or the amount of ligands. These are the reactions. What are the limitations of crystal field theory? Even though it can explain many more things than the valence bond theory, still there are some limitations to crystal field theory. Now, crystal field model is successful in explaining the formation of structures, color and magnetic properties of the coordination compound to a large extent. Here again, we can see the formation of structures, colors and magnetic properties. Okay, mainly here it explains the colors. However, from the assumptions that the ligands are point charge, it follows that anionic ligand should exert the greatest splitting effect. Now, starting as I told you, it is assumed that the ligands are considered in a point charges. Now, if the point charges are considered, the anionic ligands will exert a greater splitting effect. Now, the anionic ligand actually are found at low end of the spectrochemical series. If we state that the ligands are in point charge format, then the anionic ligand, they should show greater splitting effect. But when we see the spectrochemical series, okay, when we see the spectrochemical series, the anions, that is iodine, bromine, SCN minus, Okay, these are all the anions with minus charges, right? Now these all anions are placed at the lower energy level of the spectrochemical series. Okay, so the point charge and the spectrochemical series, they doesn't complement each other. Further, it does not take into account the covalent character of the bonding between ligand and the central atom. So there is a covalent bonding between the ligand and the central atom, right? But that covalent bonding character is not being explained by the crystal field theory. Now these are some of the weaknesses of CFT, which are explained by the ligand field theory and molecular orbital theory, which are beyond the scope of the present study. So because valence bond theory had certain limitations, we had done the crystal field theory. Now crystal field theory again shows some of the limitations, right? So hence there was ligand field theory and molecular orbital theory which are put forth. Now y'all doesn't have both of them because they are beyond the scope of your present study, so that you will see in your higher classes. Now next is the bonding in metal carbonyls. Now how bonding happens in metal carbonyls? The homoleptic carbonyl compound containing carbonyl ligands only are formed by most of the transition metals. These carbonyls have simple, well-defined structure. Now what is homoleptic and heteroleptic? Now the homoleptic carbonyl compounds containing carbonyl ligands only. Okay, they are homo. Okay, they are splitted equally. Now homoleptic carbonyls, they only contain carbonyl compounds and are formed by the most of the transition metals. Now this carbonyl have simple, well-defined structures. Okay, that is tetracarbonyl nickel is the tetrahedral. Now pentacarbonyl nickel is trigonal bipyramidal, while hexacarbonyl chromium is octahedral. So they form a simple tetrahedral, okay, trigonal bipyramidal and octahedral structures. Now decacarbonyl manganese is made up of two square pyramidal, that is MnCO5 units joined by Mn bond. Okay, octacarbonyl dicobalt, that has two CO bond bridged by the two CO groups. Here we can see this is the simple tetrahedral, trigonal, bipyramidal structures of the carbonyl compounds and the octahedral compounds. These three are the simple compounds, whereas you have Mn2CO10. Okay, there are two manganese molecules which are joined by the 10 CO molecules, each with 5 carbonyl molecules, and there is CO2, two cobalt ions which are paired by 8 carbonyl compounds. Now the metal carbon bond in metal carbonyls possesses sigma and pi character. Now the sigma bond is formed by the addition of lone pairs of electrons on the carbonyl carbon into a vacant orbital of the metals. Now the sigma bond of metal carbon, okay, is formed here. Carbonyl has a carbon, right? So this is a metal carbon. Sigma bond is formed by the donation of the lone pair of electrons present on the carbonyl carbon. So the lone pairs, okay, lone pairs which are present on this carbon, that is carbonyl carbon, the lone pairs which are present on this carbon are donated into the vacant orbitals of the metal atoms. Okay, now that is how the sigma bond is formed. Now how the metal carbon pi bond is formed? The metal carbon pi bond is formed by the donation of pair of electrons from the filled d orbitals of metal into the vacant anti-bonding pi orbitals of the carbon monoxide. Now the pi bond is formed by the sharing of electrons from the completely filled d orbital of the metal to the vacant anti-bonding pi orbital of the carbonyl carbon. Okay, here from metal the electrons are placed into the carbonyl carbon. Okay, that's how pi bonds are formed. Now sigma bonds are formed by the donation of lone pairs from the carbonyl carbon to the vacant metal atoms. Okay. Now the metal to ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. So once there is metal to ligand bonding, okay, it creates a synergic effect which strengthens the bond between CO molecules and the metal. So metal to CO, this bond is stronger. Okay. Now next is the important applications of coordination compounds. Now what are the applications of coordination compound? The coordination compounds are of great importance. Now these compounds are widely present in the mineral, plant and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgy, biological system, industries and medicines. Okay, coordination compound, they are of great importance. These compounds are widely present in minerals, plants, animal worlds and play important functions in various areas of analytical chemistry, metallurgy, biological system, industries and medicines. Now, some of them are described below. Now, first, coordination compounds find use in many qualitative and quantitative chemical analysis. Now, coordination compounds, they are used for many qualitative and quantitative chemical analysis. Now, the familiar color reaction given by the metal ions with the number of ligands, especially chelating ligands, as a result of formation of coordination entities, form the basis for their detection and estimation by classical instrumental methods of analysis. Now, since they form color, okay, they form familiar color reactions when the metal ions are involved with ligands, okay, as a result the formation of coordination entities. Now on this basis the detection and estimation of them using classical and instrumental methods of analysis is very simple. For example, such reagents including EDTA, DMG, that is dimethyl glyoxime, alpha nitroso, beta naphthol, cupron, etc. Because EDTA is a ligand. When we add EDTA to a metal ion, it will give a color, right, forming a coordination entity. And that once that color is formed, we can use various methods, instrumental methods, to determine the amount of metal ions. Okay, so this is what we do in laboratory for a chemical estimation. Now next is hardness of water. Hardness of water is estimated by simple titration with disodium EDTA, and okay, to determine the hardness of water we do a titration, simple titration with disodium EDTA. Now the calcium and magnesium ions form a stable complex with EDTA. Now when we do a simple titration with EDTA, the calcium and magnesium are the ones which causes the hardness of water. Now we can estimate their amount because calcium and magnesium, they form stable complexes with EDTA. Now the selective estimation of these ions can be done due to difference in the stability constants of calcium and magnesium complexes. Since they show different stability constants, you can determine the amount of calcium and magnesium present in the water. Now next one is some important extraction processes of metals like those of silver and gold make use of complex formation. So when you want to extract a metal like silver and gold, it is basically done by forming a complex. Now gold, for example, combines with cyanide in presence of oxygen and water to form a coordination entity of AuCN2 in aqueous solution. So gold you can extract by forming a complex with cyanide ion in presence of oxygen and water. It forms an AuCN2 complex in aqueous solution. Now gold can be separated in metallic form from the solution by the addition of zinc. So to this complex, when we add zinc, you can separate out gold in its metallic form. Okay. Now next one is the similarly for purification of metals. Okay, if you want to purify metals, you can again use the formation of complex. Okay, Purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. For example, impure nickel is converted to nickel carbonyl, which is decomposed to yield pure nickel. So again, you have to form a complex and then you can remove the pure nickel. Pure nickel from the complex. Now the coordination, next one is the coordination compound are of great importance in biological system. The pigment responsible for photosynthesis, that is chlorophyll, is a coordination compound of magnesium. Again, coordination compound has a great importance in biological system. That is, during photosynthesis we use chlorophyll, right? Now that chlorophyll is a coordination compound of magnesium. Again, in our body we have hemoglobin, the red pigment now of blood, which acts as an oxygen carrier in coordination compound of iron. So it is a coordination compound of iron. Again, vitamin B12, it is cyanocobalamin, the anti-pernicious anemia factor. Now it is a coordination compound of cobalt. Okay, so there are various coordination compounds in our body as well as in a living organisms. There are among the other compounds of biological importance, coordinate metals ions are the enzyme like carboxypeptidase A and carbonic anhydrase, catalyst of biological system. These are enzymes. Again, these are coordination compounds. Now coordination compounds are used as catalysts for many industrial processes. For example, include rhodium complex. Wilkinson catalyst is used for the hydrogenation of alkene, so it is used as a catalyst also. Now, articles can be electroplated with silver and gold much more smoothly and evenly from solutions of complexes like AgCN2 and AuCN2 than from the solutions of simple metal ions. Now again, you can use it for electroplating. Okay, complexes like AuCN and AgCN. Now, in black and white photography, the developed film is fixed by washing with hyposolution, which dissolves the undecomposed AgBr to form a complex of AgS2O3 twice. Now again, you have that black and white photograph, okay, which you have to develop into a photograph, right? You wash it in the hyposolution, that is again a solution which forms a complex. Now there is growing interest in the use of chelate therapy in medicinal chemistry. So there is use of chelate therapy in medicinal chemistry. An example is the treatment of problems caused by the presence of metals in toxic proportion in plants and animal system. So when you consume any plant or animal which has toxic metals present in them, so that toxic metals will accumulate in your body. Thus the excess of copper and ions are removed by chelating ligands like D-penicillamine. So when that excess, if you have excess of copper or iron in your body, that is removed by chelating it with ligands like D-penicillamine and desferoxylamine B via the formation of coordination compounds. So these ligands will form a coordination compounds with these metals and it will be removed out of your body. The EDTA is used in the treatment of lead poisoning. When you have lead poisoning, again EDTA is used. Now some coordination compounds of platinum effectively inhibit the growth of tumors. Okay, some of the coordination compounds associated with platinum, they inhibit the growth of tumors. For examples are cisplatin and related compounds. Okay, now here we have seen the uses of or applications of coordination compound, bonding in metal carbonyls and crystal field theory and its limitations. So here we have finished with the chapter that is coordination compounds. So thank you for watching my video. Please do like, share and subscribe to our channel.